Hello, everyone. Let's start. Today, we will continue to talk about the hardware design for deep learning. So in last lecture, we talked about the basics of convolutional neural network. We talk about the high performance, high accuracy of the convolutional neural network. Meanwhile, we also talked about the computing overhead of the convolutional neural network. You can see there are a lot of weights. A lot of weights means you need a larger on-chip buffer or on-chip memory. You also need a compute a lot of MAC operation. MAC operation means multiply accumulation. And then we have the algorithm of the convolutional neural network. Here is one example. So the algorithm itself is very simple. It's just a multiply accumulation. But we have 7 different levels of a loop. And we talk about the possible hardware solution for the convolutional neural network. CPU is too slow, so we don't consider CPU anymore. The success of a convolutional neural network, CNN, is actually enabled by GPU. So it's the baseline. It's the conventional solution for the CNN. So for more flexible and more energy efficient hardware solution, we need to consider the ASIC design and the FPGA design. So ASIC design is very expensive. But FPGA design, compared to the ASIC design, FPGA design is more flexible. So this is the TPU from Google. So it's the typical ASIC design. We also talk about the FPGA design. Nowadays, although we study the VHDL in this lecture, in this class, now the FPGA support C++. So you can directly write some C++ code on FPGA, and then they can translate your C code to VHDL and then do the things like this. One thing you need to consider is the ratio between the computation and the memory access. So how many MAC unit do you need on one FPGA is a very critical question. So you need to make sure that first you have enough hardware resource to do the computation. Second, you have a large enough off-chip memory bandwidth to support these MAC units. So in this example, we can see that, either a small number or a very large number neither a small number or a very large number of Mac unit is good. A reasonable number can achieve the best performance because you need to wisely use the FPGA resource to serve as the Mac unit and the on-chip buffer. So we also mentioned that the neural network has some error tolerance capability. So we have, 3 parameters in the neural network. One is input, the other is weight. The last one is a bias. The bias is not an important parameter. We can eliminate it actually by training, by regulation in the training. So there are only 2 critical parameters. One is the weight, the other one is the input. So we can explore the trade-off between the computing efficiency and the CNN accuracy. We have a different policy, different strategy to achieve that. The first one is because we have 2 critical parameters. The first one is to reduce the accuracy of both of them. The second one is just to reduce the accuracy of W. Because the input is more important than the weights because you have less inputs. And for the inputs is just the image. If you degrade the quality of the image, of course the accuracy will seriously degrade. So we will cover these solutions to reduce the computing overhead of the neural network with a minimum degraded accuracy. So the first one is a very natural solution, which is reduce the bit width of the parameter. For example, the bit width of weights. So let me give you more detail. So in the very first lecture of this class, we talk about the binary representation. Do they still matter? The answer is yes, of course. They matters a lot, even in this deep learning age. So for example, typically we use 32-bit floating point to represent this W, and also this X. So naively, we can just reduce the bit width of W to 16-bit fixed point. So for the project, you try to implement the adder. So apparently, you know that less width, a smaller width adder is cost you less hardware overhead, because the adder, multi-bit adder, consists of 1-bit full adder. Compared to the 32-bit floating point adder, 16-bit fixed point adder at least half the adder overhead. This is only the overhead of adder. By a smaller bit width for the multiplier, you can also significantly reduce the overhead of a multiplier. Assume that you have the fixed total computing resource or computing hardware overhead, like you have a fixed FPGA board. If you can reduce the bit width of adder and the multiplier, of course you can have more adders or more multipliers, a larger number of these computing Mac units. Consider we have 7 level loops And of course, you can increase the computing throughput and reduce the computing latency. So this is a very naive and a simple solution. And of course, to meet this challenge, to compute the neural network more efficient, now I think even both the Intel and AMD and NVIDIA GPU support integer 4 data type or integer 8. So in data type, so that you can do integer 4 or integer 8 multiplication in those hardwares to train your neural network or do the inference. They reduce the bit width even more aggressive than this 16-bit fixed point. So for a 4-bit fixed point, you can use integer to store the data. Why? Because, for example, if you have something like this, if this is your fixed point, and because this is fixed point, so the dot is always here, you can just scale all the results by 1,000 times, and then you have the binary like this. So in this way, you can use an integer to store this data. Now we will talk about some more advanced computing hardware. So people try to use some analog device to do the Mac computation. So this is one example. You can see we have a memory array here. This is one memory array. The memory array consists of 16 cells. We have four columns. We have a 4 column here. We also have 4 rows. So totally we have 16 these cells. And each cell is actually a resistor. It has some resistance. So this equation describes the relationship between the voltage, resistance, and the current. And we can rewrite the inversion of the resistance as the conductance, which is a G. So we can rewrite I equals to V multiply G. So we have a multiplication here. So in this way, we can use G to represent W. And V represent that X. Let's see what will happen. So I do some conversion. When I have this weight, I do some conversion so that I can convert it to the G. And then I can write this G to this cell. Instead of doing a multiplication, I just apply a voltage here. And then a current will flow through the cell. This is V, this is G. The current on this vertical line is the I. So here, by simply applying a current, I can do a multiplication here based on the basic physical law. This is so-called current law. I can do the same thing for this one. This is another copy of X and W. So because the current will merge on this vertical line, I have the accumulations here. So by this, this vertical line, I can at least do 4 merges. So in this way, I can calculate this. And of course, everything is here is analog. Analog means I have some noise, but it doesn't matter because the neural network can tolerate some inaccuracy. You can still get a pretty good accuracy by this analog device. So in this case, I don't even have a multiplier at all or a accumulator. I just use some resistor and some basic physical law to do the inference of the neural network to calculate this equation. And of course, I can still have some adder here to, maybe only do 3 times of this accumulation for the intermediate results. And Pierre's work also found out that because now the convolutional neural network have 5 layers, 7 layers, or 8 layers, instead of use maybe 16-bit for all the layers, I can provide a bit width to each layer. So here is some example for some small network. Each layer only have 3 bits. For some deep neural network like AlexNet, because it's more complicated, so I can provide 9-bit, 8-bit, 5-bit, 5-bit, 7-bit to different layers. So in this way, to compute different layers, you need a different bit width. Sometimes you need a 5-bit adder, sometimes you need a 7-bit adder. So Pierre's work proposed a method to, dynamically connect your 1-bit full adder together so that they can dynamically create a 5-bit adder or a 7-bit adder. So here is one example of the dynamic configurable addition or multiplication. So the basic unit here is still 1-bit full adder. They have some, reconfigurable interconnection to connect them together. So the Pierre's 3 bullets here indicate you can reduce the bit width of each weight. You don't have to represent a weight by 32-bit floating point. Maybe 4-bit, 5-bit are good enough. Another method to reduce the computing overhead is that we can remove some redundant weights. So you can see that from this figure, this is the energy consumption comparison between the addition, between the read operation from register file and read operation from DRAM. You can see that the DRAM read operation consume a lot of energy. If you have a lot of weights, you will have a lot of memory access and a lot of computation here. So instead of have this, very regular neural network structure, we can actually reduce some redundant connection between the different neurons in this neural network. But you can still get a pretty high accuracy by this structure. And of course, the accuracy will degrade, but you can still have maybe 98% accuracy. But you can see that maybe you can prove 50% connections in this network. Some people combine the idea of pruning and so-called quantization, reducing the bit width together. they do some very extreme quantization. For example, they quantize the weight into only 2 bits, which is a -1, 1 or 0. When the weight is 0, then we actually do the pruning. We just eliminate that W. And when the weight is 1 or -1, we still have the so-called 1-bit weight. And you can see that the 1-bit weight still achieve a very good very good accuracy. So the binary connection indicate the binary weights. So you can see that compared to the full procession original neural network, the error rate only slightly increased by less than 1%. Sometimes it's even better than the original neural network. Some people quantize the W into the 2 to n representation. The 2 to n representation is that, for example, this is a 2 to n representation. This is a binary form. It's actually an 8. We can rewrite this 8 to 2 to 3. If your weight is 10 or 9, you can convert your weight to 8. So this is possible. If you have a 10 or 9 as your weight, you have to do a multiplication. If you take 8 as your weight, instead of multiplication, you can do the shift to compute the multiplication. Multiply 8 is equivalent to do 3-bit right shift. For example, originally your input is 1. When you multiply 8, you do right shift by 3 bits. And this number is 8. So if you quantize your weight to 2 to n values, representations, then you can eliminate the need of your multiplier. You can just use a shifter and adder to do the accumulation, multiply accumulation operation. So you can see that by this simplification or quantization, you actually achieve very reasonable performance here. Only 1% or less than 1% accuracy degradation. But the computing overhead of a multiplier and a computing overhead, the hardware overhead of a multiplier and the hardware overhead of a shifter is the ratio between them is much larger than 1%. So this is the hardware for the shifter neural network. You only have a shifter and the addition here. So besides now for the binary connection, we just quantize the W, the weight into -1, 1 or 0. For some more extreme neural network, it also quantize the input So by quantize the input, so basically this is the binarized weight. It binarized the weight into 1 and -1. When we try to binarize the input, what we have is 1 multiply 1 or 1 multiply -1. We can rewrite the -1 as 0. In this way, we can only we use only 1 bit to represent the weight of the input. Then we have these two types of operation. This type of operation is actually a NOR operation. By one simple NOR gate, you can perform, you can do the original multiplication. And the result here is, of course, 1 or 0. So if you have this is 1, because this is a NOR operation, which is a -1, or actually it's a -1 multiply -1, you still have a 1. 0 multiply 1 is 0. So, but after the NOR operation, instead of the accumulation operation, we can have the so-called pop counting operation. The pop counting operation is an operation that counts how many 1 are there in a binary string. For example, how many 1 are there in this case, in this string? The answer is 1, 1, 2, 3, 4, 5, 6, 7. 7. We have 7 ones. So by quantize both the weight and the input into 1 and -1, we can convert the multiply accumulation into XNOR logic operation and a pop counting logic operation. So in this way, we can also significantly reduce the hardware overhead. And of course, we also reduce the accuracy. Because this method is a very extreme method, so the accuracy degradation is about 5% or 6% here. It's compared to the binary connection network, it's larger. But you can see that we can deploy this method on some IoT devices, like some camera, some drones, which they have a limited hardware overhead and a limited battery lifetime. So we can actually deploy this method into some memory, like your DRAM chips. I think this is one example of the DRAM chips. We have some accumulation. I'm sorry. We have some pop counting and XOR logic here, and we can stack multiple, layers of DRAM on the top of the logic, so that we can directly read the data to the pop counting unit to do the inference. Actually, I got this figure from some published paper, but I think this year Samsung actually exactly release some so-called smart memory stuff, which can enable you to accelerate the neural network inside some DRAM. And the point 7 here is we can create a dictionary for the weights. Instead of having a lot of weights, we can, we can use some dictionary entry to dynamically build the weights by multiply and accumulation operation. So here is one example. Instead of have several millions of weights, we can only have several K we may only have several K bytes a dictionary. By looking up the dictionary entries and add these entries together, we can dynamically construct some weights. So it's just like the quantization. So if you have a weight which is for example, a 9, if my dictionary first entry is a 4, the fifth entry is a 5, then I can use this 2 entry to dynamically form a weight which is a 9. And if you are not lucky, I have a 3 here, can I use this 3? The answer is yes, you can use this 7 to replace this 9. The key point here is that you don't have to be accurate. You just find a close number which can represent the original weight. Even you have some difference, the neural network have some error tolerance capability. It can tolerate that error. So in this way, we can have a very dense weight matrix. The last scheme I want to introduce is a so-called block circulant weight matrix. The convolution computation is actually the multiplication between two matrices like this. We have a weight matrix, we have a vector of input, and then we can do the matrix vector multiplication like this. We have a lot of accumulation, addition, multiplication during this procedure here. So if we do this in the frequency domain, what will happen? So when we get the W weights, we do a FFT. We do a FFT on these weights. When we get the input, we also do a FFT transformation on this weight. So instead of the multiply accumulation here, we can use element-wise multiplication to replace this matrix vector multiplication. The element-wise multiplication means, for example, we have a W1, W00, W01, W02. These W are the W after this fast FFT transformation. We also have X0, X1, X2. These X are also after this FFT. So the element-wise, the multiplication means we just need to multiply these two, and multiply these two. We don't need to add them together. We just have element-wise the multiplication. And then this is good enough. We perform a inverse FFT on these results, the results of this element-wise the multiplication. And then we can, get the result of this. So by the FFT transformation, we can reduce the computing overhead, particularly the multiplication overhead. So here is the computing complexity analysis. We just reduced the matrix vector multiplication. The complexity of this one is n squared, but this one is n multiplied log n. N multiplied log n is actually the computing overhead of this FFT. So the element-wise multiplication here can be ignored. The computer overhead is completely decided by the FFT. So for a very large n, apparently this number is much smaller. Any question? So if you have any question, you can email me and I'll ask me now. So the reason why I ask you to implement adder is that you can basically write your own hardware design to do the inference. For example, after you have an adder, you can write a shifter, and then you can write some test bench to perform this shifter CN computation. And of course, you need to write the activation function. But I believe this is much simpler to write the multiply accumulation hardware. You can actually also try to implement this XOR and pop counting design. The adder can be used to compute this pop counting logic. Count how many one are there in this one, this binary string. I believe writing I'm sorry, this is XOR. No, I believe writing an XOR logic gates is not complicated. So you can also try to implement this one in your project. And I will assign the requirement, this description of your project. You can pick up one, hardware here to do the implementation. Any question? If no question, we can stop today. Thank you very much.
Thank you.
Thank you.
Thank you.